Hello and welcome to Waka Breaking It Down for the AP Statistics practice test for Unit 6. This is the unit on linear regression. This is just a practice test, so it only has 3 multiple choice and 1 free response per strand instead of 4 multiple choice and 1 strand on each test. But let's get right to it. I want to go through the answers with you and just briefly point out the main features so that you can use it to study from. Number one, the main point on this is the correlation coefficient. So right here they tell you it's 0.428. Usually we use zero point 0.4 as the cutoff for weak and 0.8 for the cutoff for strong. So this is kind of close to the weak side, but it is in the moderate zone. And they also got to realize that there are two things that the correlation coefficient can give you. It gives you the strength, which I just mentioned. This would be moderate to weak. And then it also gives you the association of whether it's positive or negative. This is a positive value, so we should have a positive association with a positive slope. Those are the only two things this really gives you. It doesn't tell you it's linear, it doesn't tell you anything else. So when you go through these things, it's uh, yeah, like part A, it's talking about individual rats. On the scatter plot, we really have no idea what each individual little rat is doing. This is just an average, like this is for the average, right? This reduction, no, it should actually, it's a positive association, so it should go up. C is the answer because that's mentioning what we just talked about, right? Positive association between the two, and it's moderate to weak, right? So those are the two things it can tell you. So that's why C is your answer. So these are all like maybe telling you, oh, the association is going down, and really it should be going up, or talking about individual creatures or whatever, but we don't know the individual data points. Okay, let's go to number 2. Again, this is a correlation coefficient problem, but the main thing on this is they're saying, what if we change the units from like dollars to cents, or we double everything, or if we multiply, do something. It shouldn't change. Like the correlation is not going to change if you change the units. It just doesn't matter if you multiply by like every value, if you multiply by some number, or divide by some number, whatever. It's not as long as you do it to every single point, it's not going to change the correlation coefficient. Um, Remember, the correlation coefficient comes from that formula that has z-scores in it, right? Zx times zy, and the z-scores are always unitless. Okay, so we just have to keep that in mind when we do this. So, okay, so it's made from z-scores. Does not change when you multiply by something. All right, number 3, which one has the most influence? In other words, if I were to remove it, which one would change the slope the most? Um, E looks like it's further away from in the X direction, which usually is a tip-off for us. But we also have to make sure that we think about what the pattern is already, which looks something like that. And if it falls in the same pattern, if I take it out, it's really not going to change the slope much, right? That's where the pattern is. Right now, this D point, however, is probably pulling the slope down here, right? So if I were to take this out, it would move everything back up where it was. The E, if I take that out, it's not going to change as much as if I were to take D out. So D is your answer. That's the most influential out of all those. Not only is it away from the center, but it also is away from the pattern. Number 4, it's a residual plot. Now keep in mind this curve, we don't really know what the real thing looks like for sure. But we kind of know that there's a pattern in the residuals, right? So that's what they're looking for. What does this tell you? Well, it tells you there's a non-linear relationship. We can see the pattern. We can't tell if the association, let me try to draw like 2 possible scatter plots for you. This could look like, right, it's concave down like this, right? My data points could go like this, and then my regression model goes through that to make this residual plot, which would have a positive association. But it is possible this also goes like this, and then my linear model goes like this through it to give you the same looking residual plot. So the same residual plot can kind of come from, a couple different looks on the actual scatter plot. So we don't know from just the residual plot whether it's a positive or negative association, but we do know it's nonlinear. So that's why E is your answer. Number 5, this is re-expressing data. This is the curved data this way. So when I look at my circle, when I'm trying to decide my ladder of powers, whether to go up or down, this is the bottom left-hand corner of that, right? So that would tell me that I'm going to go down in the x's and down in the y's. So I'm either looking for square roots or I'm looking for logarithms on the x's and the y's. That's what I'm looking for. I can see a log here, but they went up in the ladders on here. This is all going up the ladder. This is going up the ladder. So the only one that has down the ladder only is B with the log of x. So that's what I would like to use to try first. Now, it's not a guarantee always, right? But that's where you would start. Okay, number 6. This one, the whole point on this one is trying to get you to think about what a y equals x line would look on here, right? So if I drew in a y equals x line, it would look something like that. And these are really important in scatter plots because this tells us where, like points above it give you a y value that's bigger than the x value, and points below it are x values that are bigger than the y values, right? For example, if I picked a point right in here somewhere, it would have an x value of 8, but only a y value of like 4. So in this case, points below the graph, which most of them are, it's saying the husband's rating is higher than the wife's rating, which means the husbands like their wives more than the wives like their husbands, all right, or something like that, right? So that's what you're looking for here in the multiple choice, which is D. Husbands tended to rate the quality of living higher than their wives did. Oh, this is quality of living, right? Okay. Right. So there's a whole bunch of other things in here that just don't match that. So D is the answer. Number 7. This is just a straight solve. You put 80 into the equation for distance. You put that in right here. Come up with whatever number this is. Just throw it in your calculator, right? And then that number is equal to the log base 10 of cost. So to undo that, you have to roll the log. So 10 raised to this power, whatever number that is, right? 10 raised to that power should equal the cost, right? So 10 raised to the power equals the cost. So when you do all that on the calculator, you should get 301. I did it to make sure, and it works, yeah. So 301. You just don't forget the log part, right? A lot of people will try to do this and get some number, and I think it comes out to something like a 2.46 or something. I don't know. Like you just have to be careful that you don't look for like they'll post this answer thinking, and you'll think, oh, that's my answer, but you forgot to roll the log or something, right? So make sure you look for those things, logs and squares and square roots and all those things. All right, number 8, you got a residual plot. We got some data here, and it's talking about the actual weight of a backpack. This particular one has 4 books in it, so we're going to do the prediction. So what I have to do is find out what the actual weight is on the regression model. Like, I don't know what the scatter plot looks like exactly, but maybe it goes like this, and all the points are around it. Okay, so maybe something like that. We have to find what that prediction is for 4 books, what the weight of that backpack is going to be, right? But then that's just a prediction. That's just a prediction. The actual data point here, like this one, is what I'm looking at. That one on the scatter plot is actually above my regression model because it has a positive residual. It looks like about a positive 2 about. So I'm going to use 2 about. Okay, so the model will give you one number, but you have to add 2 to it to get to the real backpack weight, right? This is the prediction, the real one's here. So this is what we're looking for in reality, but you need that prediction to start. Okay, so you put that in the calculator using the slope. So we take 0.53 times 4. Half of 4 is like 2. You can almost do it in your head. That's about 2, maybe a little bit more than 2. And then I have to add the y-intercept to it. So 10.53 plus 2 point something, that's like 12.6 or something, 12 and a half, 12.6, something like that, which is tempting to put D, but you have to remember that the residual is positive and the actual point is 2, what is this, pounds? Yeah, 2 pounds above the regression model. So you get something like 12.6. You got to add 2 to it to get to like 14.6. And then that's why the answer is 15. Okay, I explained that there. Number 9. We have just some statistics here. And the point on this question is to use the formula R times SY over Sx to get your slope. That is the key to this one. And that will give us our regression slope. So they give us our standard deviation in the X. They give us standard deviation in the Y. Okay. So I'm using those. It's just 9 over 2.3. I have to multiply that by R, however. I don't have R, I have R squared. So I have to take the square root of that number to get to R. 0.5625, throw that all in a calculator, and you will have your slope. And in this case, the slope should come out to 2.93, right? If I saw that any of these others were also 2.93, I would have to go further and check something else using the means. So I'll do that just to show you, or I'll explain it. But in this case, like 2.93, this is the only one that has 2.93 for the slope, so that becomes my answer right away. I would move on. But if many of them have 2.93, what you're supposed to do is use the means for the x and the y and plug those in to get your y-intercept. Now, in this case, we could use them to check our answer. So if I put 4.5 in for the additive, right, and I calculate this, it should come out to 32 over here, right? So you just have to check that, or you can use that once you found your slope to find out what your y-intercept is. Like maybe you don't know what your y-intercept is and you need to check that and find that. Right? So you can use the standard deviations and R to get your slope, but then you can use the means of the two lists to get your y-intercept. Number 10. Okay, so we're on to free response now. This is just a regression with the customers in line and how long it takes you to get there. We have a bunch of data, right? I got the slope, 174. I got the y-intercept, that's 79 or 73 almost. And I have my R squared here. Remember, we don't use the adjusted, and we won't do any of this stuff until we do inference next unit. Okay, what are they asking? Identify and interpret the intercept. Okay, well, that's the 72.95. And remember, that's just your starting amount, basically. On the graph, it's right here, right here. So if I had 0 customers in line, the model would predict that the time I'd have to wait in line would be approximately 72.95 seconds. Now, it could make sense in this situation. Like maybe you still have to wait for the teller or whoever, the person, the checkout person, to kind of get ready for you. So sometimes you have to wait for them to be ready or something. So it could make sense in this situation. I don't want to say it doesn't or couldn't, because it's possible you don't have anybody in front of you, right? That is possible. All right, so next they want you to interpret the slope. You can see here our slope is 174.4. So the model is predicting that for every 1 increase in the number of customers in line, for every 1 increase, on average, the model predicts that the time that you'll have to wait will increase on average by 174 seconds. That's a few minutes, right? Okay, so there's a different couple versions there you can read. Okay, now we're interpreting the coefficient of determination. That's the r squared that you see in the readout here. Okay, so how do we say that? Well, remember, this is the percent of the variation that you're removing because you made this association. So in the beginning, we had variation that started all the way from up here, all the way down almost to zero, right? So this was our initial variation to begin with. But now, since we made this association, we have a lot less variation going on wherever you look. There's less variation. Well, how much was removed? 73% was removed, and that means about 26, 27% is remaining. So that's what we're going to try and say here. So uh, this value indicates that 73.33% of the variability in the time it takes customers to finish checking out, including the time of the waiting line, can be explained by knowing how many customers are in the line in front of the customer, right? So in front of you. Yeah, so it's 73% of the variation can be explained by that association with the number of customers. All right, part D here. So this is one of the points was determined to be an outlier. Which one would it be on this scatter plot? So when I look at the scatter plot, it looks like this one would be the outlier. There's three directions we have to check. We check in the x direction. So I go to the bottom and the top of my data and my mass of my data and see if there's anything outside of that. There's nothing outside in that direction. I look in the y direction and I look this way and I say, is there anything outside of that direction? No, there isn't. And then I check the residuals. So I don't have a residual plot, but I have to kind of imagine like most of my residuals would graph like that. And if I turn that sideways, right, most of my data points would be right around that. Okay. But this point down here would be like way down here as an outlier. So that point right here should be considered an outlier in the residual direction. So that's what we're saying here. So the outlier at x equals 3, close to 0 in the y direction, would be the one considered an outlier in the residual direction. All right. It's lower than all the other data points relative to the linear regression model. So that's why it's considered an outlier. Okay, number 11, free response. They give us a residual plot. This one's a little different, little weird, because on the x-axis, they do not put the x variable. They actually put the y variable there. So this is the percent killed on the bottom, which is weird. And then they did the residuals compared to those. Very strange, right? So they got their residuals, but instead of plotting them against your number of teaspoons, they plotted it against the percent of the weeds you're killing. That's a little different. So it works the same way, but a little different. Okay, so what's the equation? Well, that's okay. We can do that. Here's our slope, 24.39. Here's our y-intercept. And I know that because that's what the explanatory variable is next to. And it just says constant for the y-intercept. So these are the numbers. Out of all those numbers, like there's a lot of extra stuff here. You don't need any of that other stuff. All this is just gone. We don't need any of that, right? You just need that stuff at the bottom left. So you just got to look for it. All right, so we write our equation. Make sure you're putting in context inside of there. Make sure you're putting a hat on top of your response variable. If you call this x and y, on the side, you have to define those variables like x equals blah, 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 y equals blah, 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 blah. That's why we say define any variables. So I think it's easier, just don't even use the variables in the begin with, and then you don't have to define them. Okay, part B, use the given residual plot to check all the conditions. So we just want to know that it's straight. We want to know that the residuals have a nice kind of random pattern to it. And we don't want any fanning. We don't want any outliers. So when I look at this, I'm like, no, this is not a good model for a linear regression, right? So a linear model should not be used. There's a clear pattern in the residuals, that curved pattern. So, and the points are just not uniform and evenly scattered. So it's not a good fit. The main thing you just need to mention is the pattern, right? It's like in geometry. If you can find a counterexample, then you're pretty much done. Okay, but we want to be thorough. This is AP, right? Okay, part C. So if someone uses this equation, whether they should or not. So that's your tip off to just say, hey, we know it's not a good model, but use it anyway. Okay, so to predict the percentage of weeds, blah, blah, blah. So we're going to use 2.6 teaspoons of weed killer. So you just plug that in the equation, come up with a number, and then, okay, so they're talking about would it be an underestimate or overestimate with the model, right? Would you get an under or overestimation? So this value is an estimation, right? Here's where this weirdness comes in. This is the y value. When you do your regression, I'm not actually looking for 2.6 on that graph. I'm going to look for the 42.8 on that graph, right? 42.8 is right here. You can see that would, like, the model is going to be like this, right? So the model is predicting something up here. The real data points would therefore be below that model, which means they have negative residuals, right? So this is your zero line. Oh, sorry, that's your regression line, right? So at 42, that would be your prediction. These are below, so they have negative residuals. So if it's a negative residual, that means the actual data point is below the regression model. So the regression model is overestimating, right? Which is what it says down here. You can see down here it says overestimate, right? So looking at the residual plot, looking for that 42.8, we can tell that all the data points are negative residuals, and we will be overestimating there then. Okay, Tyler says we should use 2 linear regressions and to split it up. So do you agree with that? And you should say yes. Make sure you answer the question yes. Why? Well, if we split data like right about here, I could have one linear model that goes this way and another linear model that goes this way. Now I know this is residuals, but it's going to work the same way on the actual scatter plot. Even if you redo this, you don't have to try to figure out what the scatter plot looks like. Just know that, oh, this is going to be like, this is the regression model now, right? Something like that. So this is something we could graph. We could graph those two things. So I would say for any values that have a predicted value of about 40 and below, I would make one regression model, and then when 40 and above, I would make a different regression model. It's just a little weird because those are the predicted values, not the inputted values. Okay, so split domain. Okay, last problem, number 12, free response. Again, so write the equation of the linear regression model. So you just have to put this stuff into your calculator, into an XY table, right? You got X's as your hours and your Y is your concentration, and just put those in 2 lists, run your linear regression on your TI-Nspire, and you should get this model out of it, right? Again, make sure you get hours and concentration, and you put a hat on it like we have here, okay? Yeah, if you're having trouble with that, seek some help from your teacher or your friends or something. It's just a straight throw it in the spreadsheet and do the regression model. Okay, so to get residuals, you can just push the button, right? So I can, like, real quick just show you where the buttons are, but I would put some data in here, oh, this is X, this is Y, just naming it. And I'm just going to make up some fake data real quick just so I can do it. 5, 6, 7, 9. Okay, whatever. So when you plot these things out and you have your regression and you have your data plotted, right? We go to analyze and we do regression, and that gives you regression. Then you can go to residuals and show residual plot. And this is what you need to draw on your paper. You're going to have, on a test, you're going to have to do it by hand, right? So it should look something like this, where you have residual labeled, you have your zero line, and then you can plot your points around it. So in this case, this is what the residual plot should look like if you did it right. Okay, so is linear a good fit? No, it is not. Remember, we're working with a lot of problems and curved data, right? So there's a pattern in the residuals again, so not a good model. Okay, so what should you do to try to make this better? You have the actual data. I know what the actual scatter plot looks like. I can even look at this 1, 2, 3, 4, 5, 6, 7, right? So in my head, I can be like, well, we start off at 42, we go all the way down to 28, and then 19, 13, 9, 6, 4. Just even in my own like quick little scatter plot, I can see it curves like that, right? So I know that that's the bottom left-hand corner of the circle for the ladder of powers. And I know that I'm going to want to go down in the x's and down in the y's. So I'm looking for logarithms or square roots, something like that. So they offer me two possibilities. This one has a square that's going up in the power, which I don't want to do. I want to go down. So you should choose model 1. So so you should just say, I'm going to choose model 1 to re-express the data. And then when you do that, it should work for you. When you do model 2, it'll still have a curved pattern. This bottom left of a circle tells me that that's what I should be going down in powers to try and straighten it out. Okay. Use your choice. So whatever you chose in part C, you can get follow through. You want to estimate what it'll be after 9 hours. So just put 9 into that equation, right? This is the one with the log. Get your number on the right-hand side. You can see I did that there. And then you have to roll the log, right? Roll the log to get the concentration out of it. So get rid of the logarithm. So that's 10 to the 0.2699 power. I just leave all the decimals, don't round too much. Powers can be really finicky with decimals. Okay, so when you put that all in, you should get 1.86 as your answer. Make sure you put units on it and all that stuff. Now, you made your prediction, but you're supposed to recognize that, hey, wait a minute, 9 hours, if I go back up, is not part of my domain. My domain only went from 1 to 7. That's something you just have to check on your own. You just have to check it every single time to see if you're kind of extrapolating. So we have to say, well, that's what my number would be, and you should actually go ahead and come up with that number. But you have to say something about it being extrapolating. So it's like, wait a minute, it's outside that domain of 1 to 7. We can make the prediction, but we're going to have very low confidence about that prediction. Okay, that's it. That's the practice test. Good luck on your real test. Talk to your teacher and your friends while you're studying if you have questions.